Every piece of software you run operates under a delusion. The code demands infinite memory and endless processing power, but hardware is rigidly finite. There are only so many transistors and only so many clock cycles per second. The operating system exists to resolve this tension. It is, at its core, a multiplexer. Its entire job is to divide physical time, meaning CPU cycles, and physical space, meaning memory and disk storage, among competing threads of execution. To maintain order over this chaos, the OS kernel enforces strict governance across 5 distinct domains. These pillars are process management, synchronization, deadlock prevention, memory management, and file systems. When a system crashes or latency spikes, it is rarely a physical hardware defect. Instead, it is a mathematical breakdown within one of these 5 arbitration frameworks. To write code at scale, you have to understand exactly how the arbiter makes its decisions.
The primary objective of CPU scheduling is a constant mathematical balancing act. The kernel must maximize total system throughput, getting as much work done as possible, while strictly minimizing the average waiting time for any process sitting in the ready queue. To keep a system responsive, modern kernels use preemptive scheduling. The OS forcibly interrupts a running process to give time to another. But this requires specific hardware interrupt support, and every time the OS pauses one thread to load another, it incurs a time penalty known as context switching overhead. Let's look at exactly how a preemptive algorithm handles a highly specific system state. We have 4 CPU-bound processes arriving at unequal times, with varying CPU burst lengths. We'll use the shortest remaining time first algorithm. Process 1 arrives at 0 milliseconds. The ready queue is empty, so it immediately begins processing its 10 millisecond burst. But at exactly 3 milliseconds, a hardware interrupt fires. Process 2 arrives, requiring only a 6 millisecond burst. The scheduler compares this to process 1, which still has 7 milliseconds remaining. Since 6 is less than 7, process 1 is preempted and forced to yield the CPU to process 2. This cascade continues. At 7 milliseconds, process 3 drops in with a tiny 1 millisecond burst, instantly preempting process 2. At 8 milliseconds, process 4 arrives, needing 3 milliseconds, bumping everyone else down the line. The CPU is constantly re-evaluating the queue to find the absolute shortest remaining time. When analyzing this execution, we must distinguish between waiting time and turnaround time. Turnaround time is the total duration from the moment a process arrives to the moment it finishes, which intrinsically includes all the accumulated waiting time sitting idle in the queue. Shortest remaining time first is heavily utilized because it guarantees the mathematically proven minimum average waiting time for any given set of processes. The cost is that processes with long execution times risk starvation, waiting endlessly while shorter bursts cut in front of them. While the scheduler manages time, it creates a new hazard when managing shared state. Because concurrent processes are rapidly swapping in and out, they frequently attempt to read and write to the same exact variables in memory. Any segment of code where shared memory is accessed is called a critical section. For the system to remain stable, a critical section must be protected from simultaneous execution. Early attempts at solving this relied purely on software. Imagine 2 processes using simple Boolean variables, var_p and var_q, both initialized to false, to signal when they want to enter a critical section. The logic seems sound until you factor in the CPU scheduler. A perfectly timed context switch right after process X sets its flag, but before it actually enters the critical section, leaves an opening. Process Y runs, sets its own flag, and both processes bypass the checks, entering the critical section simultaneously. The data is now corrupted. This proposed software-level solution fails to guarantee mutual exclusion because the flag-setting instructions are not atomic. They can be interrupted halfway through. To solve this, synchronization requires hardware-supported primitives. The system uses strict tools like non-reentrant locks, ensuring that the act of acquiring the lock is a single, uninterruptible physical operation. Without strict atomic locks, the unpredictable interleaving caused by CPU scheduling guarantees that concurrent software will overwrite its own logic and corrupt its own state. But synchronization introduces an inverse danger. If locks are applied randomly without a strict global ordering, processes can easily trap each other. This specific state is called a deadlock. It occurs when every process in a given set is waiting for a resource that is currently held by another process in that exact same set.
Nobody can move forward, and nobody will release their locks. This is distinct from a live lock. In a live lock, processes continually change state, yielding and reacquiring resources to avoid a collision, but they still fail to produce any actual computational work. A system can only suffer from one of these states at a time. Deadlock and live lock are mathematically mutually exclusive conditions. The OS kernel implements specific policies to break these loops before they form. A common mathematical constraint is requiring a process to release all currently held resources before making a request for a new one. Deadlocks aren't random glitches or bad luck. They are deterministic, topological traps caused entirely by circular dependencies inside the system's resource allocation graph. Beyond processing time, the OS must arbitrate physical space. Physical RAM has always been a strict, hard boundary for executing code. Programs must be loaded into memory to run, and space runs out fast. The kernel hides this limitation using paging and virtual memory. The OS assigns every single process a massive, perfectly contiguous virtual address space that doesn't actually exist on the hardware. The bridge between the illusion and reality is the page table. This is the kernel's translation dictionary. It maps neat 4 kilobyte virtual pages directly to heavily fragmented physical frames scattered across the actual RAM. And every row in this table carries critical metadata. Take the valid bit. If a process requests a page and the valid bit is set to 0, it means the data isn't in RAM at all. This triggers a hardware trap called a page fault, forcing the OS to pause the process and fetch the data from the much slower hard disk. Then there's the dirty bit. When a process modifies a page in RAM, this bit flips. It signals to the operating system that this specific frame contains unsaved changes, and it must be written back to the physical disk before the OS is allowed to erase it. And the reference bit tracks recent usage. When RAM is completely full, the page replacement algorithm uses these bits to figure out which pages are cold and therefore safe to evict to make room for new data. Virtual memory is a sophisticated sleight of hand. By trading microscopic, calculated disk access latencies, the kernel gives every single process the illusion of infinite, unbroken memory. Exactly like physical RAM, physical disk space is fractured. Files are almost never saved as continuous strips of magnetic tape. They are broken into tiny, scattered blocks across the disk platters. To keep track of these pieces, Unix file systems use a data structure called an inode. Let's look at the exact engineering parameters. Imagine a disk formatted with 128-byte blocks, where every block address pointer requires exactly 8 bytes of space. Under these specific constraints, what is the maximum possible size of a single file if its inode contains 8 direct blocks, 1 indirect block, and 1 doubly indirect block? First, establish the baseline ratio. If a physical block is 128 bytes and an address pointer takes 8 bytes, dividing the two tells us that one single block can hold exactly 16 pointers to other blocks. Now calculate the hierarchy. The 8 direct blocks point straight to data. 8 blocks times 128 bytes equals 1024 bytes, or exactly 1 kilobyte of data. The 1 indirect block is a pointer to an index. It points to a block that holds 16 pointers. Those 16 pointers hit data blocks. 16 times 128 bytes gives us another 2048 bytes. Finally, the doubly indirect block. One pointer hits a block of 16 pointers. Each of those points to 16 more pointers. 16 times 16 is 256 data blocks. Multiply that by the 128-byte block size, and we get 32,768 bytes. By combining these tiers, 1024 plus 2048 plus 32,768, the file system effortlessly tracks a logical file of exactly 35,840 bytes, managing hundreds of scattered physical sectors through one unified descriptor. Process scheduling, synchronization, deadlocks, memory, file systems. These are not isolated modules. The kernel is a deeply integrated, highly reactive ecosystem. A single execution triggers a cascade across the architecture. The CPU scheduler preempts a thread. The system swaps to a new process, which requests an address that triggers a page fault in memory. That page fault forces a disk read, which must navigate the inode tree of the file system. But to read that file, the thread must first acquire a non-reentrant lock to maintain synchronization, perfectly ordered to avoid a system-wide deadlock.
To engineer software at a professional scale, you have to look past the high-level code. True system design requires understanding this relentless, microsecond by microsecond arbitration of physics and mathematics happening deep inside the kernel.